In this video, what I would like you to do is to follow along and help derive the range equation. And we're going to start this off. You're going to take advantage of the pause button and work this way through, if you would, and get you some experience on how to do this. This all stems from the idea if we have some kind of projectile, and I want to be able to figure out at what angle does this projectile launcher, this tank, have to fire to hit an object at a known distance away. So what we would do is we would use our equations for displacement in the x and displacement in the y, and I'm going to write this out in terms of launching speed out of the tank. So the displacement in the x would be equal to vx times t, while vx would be the launching speed out of the tank times the cosine of theta. In the y direction, we would be using the 1/2 gt squared plus vyt, but vy would be the launching speed out of the tank times the sine of theta. If you look at this, displacement in the x direction is a known quantity. We would know the distance, the range from the tank to the truck. We would know the launching speed of the projectile out of the cannon. What we would not know is the angle, which was what we're interested in, and we don't know the time. So we have two equations and we have two unknowns. So there's lots of different ways to solve these. I'm going to be using the elimination method, and we are going to solve for a variable. Actually, that's not true. We're going to be using the substitution method, and we're going to substitute a variable out. So we have to take one of these equations, and we are going to substitute out the t. So we look at these, which one's easier to solve for t? Well, it's going to be the dx equation, because it only has one t in it. So if I want to solve this for time, I divide the v0 cosine theta over to the left side, and so I got t by itself, and this is dx over v0 cosine theta. I am then going to plug dx divided by v0 cosine theta into the times in the dy equation. I'm going to code that in red. This is where I want you to pause this, and I want you to do this replacement and get this set up and ready to go on to the next slide here. So after we've done our replacement, here's what we have, and now it's time to do a little bit of cleanup. So the first thing I'm going to look at is this right side. I've got a v0 on the outside here, and I got a v0 on the bottom here. Those v0s will cancel out. That leaves me with a sine theta. I'm going to move the sine theta on top here, and so we got dx sine theta over cosine theta. And that's all I'm worried about is this term right here. Now, some people might say, well, I got sine theta over cosine theta. That's the tangent of theta. Actually, that's a mistake. We actually are going to need the cosine and sines here in a little bit, so we're not going to touch those. The next cleanup step I'm going to do is this square. I'm going to distribute the square across here, and then I'm going to distribute the g and the 1/2 and put everything one over the other. So the squares, we got dx squared, and we're going to square the v0, and we're going to square the cosine. And so there's my dx squared, my v0 squared, my cosine squared. The g is a multiplier, so it goes on top, so there's where the g is. And the 2 is a divider, so it goes on the bottom right here. And so I clean this step up here, and I got g dx squared all over to v0 squared cosine squared theta. And then we have our plus dx sine theta over cosine theta. And a lot of people start looking at this and they're like, wow, this is getting a little bit more complicated, but we're about ready to clean everything up and get rid of a lot of stuff here. At the beginning, we said that the displacement in the y direction is 0. So in this case, since dy is 0, we can set this equal to 0. Hopefully you've done your algebraic manipulations here and taken some advantage of pausings. And let's take this over to the next slide and let's do some maneuvers. So this is what we were left with. I'm going to take this right term, dx sine theta over cosine theta. I'm going to subtract it over to the left side, and I want you to do the same. And so that gives me negative dx sine theta over cosine theta. Since I subtracted it, there's a negative sign there. And then I'm left with this term right here. I haven't adjusted it at all. Once I've done the subtraction, now I can start doing some cleanup. And so you notice there's a dx here and a dx squared here. So I can cancel out a dx and the squared. There's a cosine here. So imagine if I multiplied by cosine, I can get rid of the cosine and the square. So I can divide by dx and get rid of dx and the square. So the square terms goes away, and the square on cosine goes away. So I'm left over here on the left side with the negative sine theta, because I just got rid of my dx and my cosine. I got rid of the squared on dx. I got rid of the square on cosine. And now we're starting to look a little bit more simplified. That's why we didn't want to turn this into sine theta over cosine theta's tangent, because I needed to multiply by cosine to get rid of that cosine squared. All right, so now I'm going to take this whole denominator here, 2 v0 squared cosine theta, and I'm going to multiply it over here to the left-hand side. I'm going to collect my trig functions here. So I've got my negative sign, I've got the 2, I've got the v0 squared, and I collected my sine theta, cosine theta. And right about now, it looks like we're stuck. I mean, what else can we do? We'd like to get the theta as one term, and it looks like algebraically we're stuck, but we are stuck algebraically. We just need to bring in some trig identities. And so if you study your trig identities, there's a trig identity that says that 2 sine theta cosine theta is equal to sine 2 theta. This is a double angle formula. Well, here's my 2. Here's my sine theta cosine theta. So I'm going to copy out this onto the next slide, and then I'm going to replace what's in red with sine 2 theta. So there's the 2 sine theta cosine theta. I've now made that sine 2 theta. I'm still left with my negative v naught squared is equal to g dx. All I'm going to do now is I'm going to divide by the g, and this is the range equation. This range equation tells you the distance fire is equal to the firing speed squared of the projectile launcher times the sine of 2 theta divided by g. This negative sign out in front of here is going to cancel the negative sign of g so that everything is positive. And this is the formula that you can use to calculate for theta. Now there's some caveats to this. It only works when the displacement in the y direction is equal to 0 because that's what we had to assume on a previous slide. And from the basis of our tank problem, it was 0. If it's not 0, you're still going to use this substitution technique to solve for things. It just doesn't derive into the range equation. So you still have to know how to do this if you have problems where dy isn't 0. You're going to have to do this 2 equation, 2 unknowns. And it's difficult. That's why I want you to be able to derive this on your own and get this math down. Thank you for your time.